Welcome to the Metabolic Classroom. I'm Benjamin Bikman, biomedical scientist and professor of cell biology. Today, we are exploring a topic that I would say is both underappreciated and incredibly important. And that is fat and its hormones. When most people, and probably you if you're being honest, think of fat tissue, they picture something inert, just a storage depot for extra calories, passively taking them in and passively letting them out. But fat is so much more than that. It's a dynamic endocrine organ, actively producing and releasing dozens of hormones that influence nearly every process in your body, sending distant signals from the fat to far-flung parts of the body. They affect various processes, from how hungry you feel to how your blood vessels function. Fat tissue is a major player in cardiometabolic health. To date, researchers have identified roughly 50 distinct hormones secreted by fat tissue. Now, these hormones there are so many that they're given their own category name. Adipokines, of course, deriving from the term adipose or adipocyte, which is the technical term for fat tissue or fat cells. Today, we'll focus on some of the most metabolically significant ones, including leptin and adiponectin, but also a cardiovascular relevant hormone, PAI1, along with a few others just to round out the picture to help you get a really firm idea as to how relevant fat tissue is with regards to its hormones and whole body health. We'll also explore how these hormones differ depending on where fat is located, subcutaneous, visceral, or brown fat, and why that also matters. So grab a notebook or just settle in and let's get started discussing fat and its hormones. Now, most importantly, adipose tissue or fat isn't just a passive storage site for calories. It is an active endocrine organ, like I mentioned, communicating, sending these signals with the rest of the body through the hormones and other signaling molecules. These adipokines number into the dozens, like I said, and there are, in fact, even hundreds of other what's just called bioactive compounds that haven't quite earned the status of hormone, but many of them very well may. Altogether, they influence myriad processes affecting things from the brain to muscle tissue to inflammation and immune function, and as I mentioned, heart health. But all of this is to say that fat tissue really does occupy or sit at the middle of a bit of a central hub when it comes to the metabolic network. Now, having said that, not all fat is the same. You've got subcutaneous fat, that layer just under your skin, visceral fat, which wraps around your internal organs, and brown fat, a specialized type that burns energy to produce heat. This is mostly sprinkled throughout the rib cage, or what we would call the thoracic cavity. Each of these fat depots has a distinct hormone profile, and we'll go through these differences as we explore the different fat tissues. But before that, let's focus on some of the key hormones that fat produces and what they do in the body. So first, leptin. Let's talk about leptin, one of the most well-known adipokines. It's actually a pretty recent discovery, discovered in the mid-1990s. Leptin is often called a satiety hormone because it signals to your brain that you've had enough to eat. Now, I personally have some reservations with calling leptin the satiety signal. I actually think in the grand scheme or spectrum of satiety hormones, leptin is a more modest one. It's also a more delayed signal. I think hormones like GLP-1 ought to be more of the primary focus when we talk about satiety. Nevertheless, leptin absolutely does have an influence on satiety, but I would say in a more long-term view rather than an immediate signal where you have eaten a meal and you push the plate away, deciding that you're done. Now, having said all of that, let's just I remind you that leptin is produced primarily by fat cells and travels through the bloodstream to the hypothalamus. That's the region of the brain that regulates hunger and energy balance. When leptin levels are high, it tells the brain, hey, you've got plenty of energy stored, no need to eat more. Now, that's an important distinction because perhaps GLP-1's signal, just to make a bit of a an informal comparison, might be more of, hey, there's stuff in the intestines you don't need to eat anymore. Leptin isn't going to be that signal. That's why I'm suggesting that it's more of a long-term satiety signal. It's generally going to be suggesting to the brain, hey, we have a lot of energy here on the body in the form of fat tissue. We don't need to add to it necessarily. So that might, in the long term, provide a bit of a subtle pressure on appetite, signaling that the body has enough. Now, here's where it gets interesting. Leptin levels are directly tied to how much fat you have. The more fat tissue you carry, the higher your leptin levels. In someone with obesity, leptin levels can be sky high, but here's the catch. Many of these individuals have leptin resistance. It's like the brain stops listening to leptin signals, so appetite stays high, hunger stays high, satiety is nowhere to be seen, and even there's changes in energy expenditure like metabolism. Now, leptin does a lot more than just influence appetite and hunger. It also has direct effects on things like mitochondrial function. But I'm not going to get into all of that because this isn't explicitly a metabolic classroom on leptin. But the leptin resistance is a hallmark of metabolic dysfunction and a key driver of weight gain. One of the studies here that I have in the show notes is a 2009 study by Myers and colleagues in the very good journal Cell Metabolism, and it really nailed this down, showing how leptin resistance disrupts hypothalamic signaling, contributing to obesity. It's a landmark paper that helped us really understand why high leptin doesn't always mean less hunger. Now, in contrast, when fat mass decreases, like during weight loss, leptin levels will go down. This is why leptin or weight loss can actually make you over time start to feel hungrier. That imagine a person who's starting to lose weight, they're successful, but then hunger starts to work against them. Part of this could be that as fat mass goes down, leptin goes down, and that's, like I was mentioning, some of this long-term, more chronic regulation. So just to try to check itself. It is a survival mechanism, we would say, although we may also say that it begins to work against our efforts at weight loss. Now, a moment ago, I mentioned that leptin has effects that go well beyond regulating hunger and satiety. Let's focus on that a little bit as we transition into discussing leptin's differences across the two sexes, because there are meaningful differences. Women tend to have much higher levels of leptin than men, even when matched for body fat percent. Let me state that again. The easy thought there might just be, well, it's because women have more body fat than men do. Yes, by design, women do have more fat than men do on average. But even if it were the same body fat percentage, women will still have more. There's two reasons why this might be. First, women naturally carry more subcutaneous fat. That's the fat that produces more leptin than, say, visceral fat does. And men will have more visceral fat on average relatively than they do subcutaneous fat. So the difference in fat storage depot location between the two sexes would explain that. Now, second, estrogen levels, which are, of course, higher in women, increase leptin production. This can explain why women can sometimes report differing hunger patterns than men. All right. Now, one other point. Now that I've introduced the sex differences with regards to leptin, let's continue on that theme, because one other very important, and in fact, I argue the most important effect of leptin is how essential it is to fertility. What I mean by that is, if I could have rewritten and could rewrite all of the endocrine textbooks, all the endocrinology textbooks, I would not describe leptin as a satiety signal at all, or maybe mention it as a secondary effect, because there are other satiety signals, like I've mentioned GLP-1, and there are more than just that. But there is nothing that can make up for the loss of leptin when it comes to fertility. Now let's bring this back to fat. Insufficient body fat can lead to such low levels of leptin that you then have infertility. And in fact, people with leptin mutations, humans with leptin mutations who do not make leptin, yes, they will become very, very obese. very early. But at the same time, they are infertile. They will not ovulate or they will not produce functioning sperm. In fact, when we work with leptin deficient mice, we cannot breed them if they are what's called homozygous. If they have two mutations of the leptin gene, then they cannot reproduce. So the lack of leptin will result in women, it will halt ovulation, it will stop menstrual cycles, thereby preventing fertility. In men, there's a similar effect, albeit in the male categories, of reducing testosterone production and impairing sperm production. So altogether, if you have a body with inadequate fat mass and the female body is more sensitive to that loss, you have insufficient leptin, and then you effectively deprive the body of an essential fertility signal, and thus infertility follows. All right, that's enough on leptin. Next, let's move to adiponectin, another heavyweight in the adipokine world, albeit one that is much less famous than leptin. Any average individual has heard of the hormone leptin, and almost no one's heard of adiponectin, but it is still a heavyweight and one worth mentioning. Adiponectin is unique because it's one of the few hormones that's actually lower in people with more fat mass. Unlike leptin, which increases as fat mass increases, adiponectin levels drop as fat tissue expands, especially in obesity. This makes adiponectin a key player in metabolic health. Adiponectin is relevant because it is a metabolic multitasker. First, and the effect that I first became familiar with as a scientist is that it enhances insulin sensitivity. In particular, it does so by breaking down a molecule in cells, ceramides, that promote insulin resistance. So ceramides are a direct intracellular mediator of insulin resistance. If ceramides go up, they are directly blocking the insulin signal, thereby creating insulin resistance. However, adiponectin activates an enzyme called ceramidase. You hear the word ceramide in that word, in that enzyme. It is an enzyme that breaks down ceramides, thus restoring insulin sensitivity. But this is why low adiponectin levels are often linked to insulin resistance and type 2 diabetes. Second, adiponectin has anti-inflammatory properties, reducing chronic inflammation that can drive things like heart disease and other things like insulin resistance. And then third, it supports fat metabolism by promoting the breakdown of fats for energy. This can help prevent lipid accumulation in a way that I've referred to and others do as ectopic fat storage, where it can promote fat loss or fat burning in tissues like the liver or the pancreas, these tissues that are ill-suited for long-term fat storage. Now, an interesting paper conducted by some of the authority in the realm of adiponectin was in 2014 by Turer and Shearer. And Phil Shearer, Scherer, is really the worldwide authority on this topic. They published a great paper in Diabetologia, which highlighted adiponectin's protective role, showing how it improved insulin sensitivity, reduces cardiovascular risk in animal models and humans. And their work really does underscore why adiponectin is such a critical hormone for metabolic health. In a healthy person, high adiponectin levels are a sign of good metabolic health for all the reasons I've mentioned. But in a person with poor metabolic health, or we would say where fat has started to work against them, you will see lower or plummeting levels of adiponectin. And then in that case, these protective effects are lost, contributing to a cascade of some metabolic disarray. Interestingly, weight loss, especially with visceral fat loss, can boost adiponectin levels, restoring some of these benefits. So adiponectin is a hormone we want more of, but it's one that fat tissue produces less of when it's overgrown. It's a classic example of how fat's endocrine function can go awry and thus contribute to metabolic disease. Now, that's enough about metabolism. Let's talk a little bit about cardiovascular function, although these sorts of things are heavily related. And in fact, this is a perfect example of how metabolism in the form of fat tissue can affect cardiovascular function in the form of a clotting culprit. All right, let's talk about PAI1, or plasminogen activator inhibitor. This one's less famous than all of them, but no less important, especially when it comes to cardiovascular health. PAI1 is a hormone produced by the fat, even more so by visceral fat, and it plays a role in regulating blood clotting. Here's how it works. PAI1 inhibits the breakdown of blood clots by blocking a protein called tissue plasminogen activator, or TPA, which normally dissolves clots. Now, I'm mentioning a lot of acronyms here, so if you have to pause and rewind these things to get that. But let me say that again. So PAI1 inhibits the breakdown of blood clots by blocking the actions of another protein enzyme called tissue plasminogen activator. And again, that molecule, TPA, is what it's usually known as, acts to break down clots. So you're inhibiting this clot breakdown molecule. So the high PAI1 makes the blood more prone to clotting. It's making clots linger longer. And of course, if you have more blood clots, you're increasing the risk of things like heart attacks, strokes, and other blockage or thrombotic events. This is why elevated PAI1 is a major concern in obesity and metabolic syndrome, where visceral fat accumulation will drive its production. Now, unlike adiponectin, PAI1 levels do rise as fat mass rises, again, especially visceral fat. This does make PAI1 a pretty reliable biomarker of metabolic dysfunction and, in particular, visceral fat accumulation. It's also influenced by inflammation, which is often high in obesity. So it can create a bit of a feedback loop that will worsen cardiovascular risk. A pretty compelling study in 2003 by Alessi et al. In diabetes showed that visceral fat is a major source of PAI1 in obesity, directly linking fat distribution to clotting risk. These findings are very helpful in us understanding just why is it that people with mounting obesity levels have such a higher risk of heart disease. So this is compelling, and it's another view here, because what PAI1 allows us to do is provide a direct link between excess fat tissue and heart disease. That means it's not just about cholesterol or blood pressure, these overly or oft looked at variables, but the hormones coming from fat can actively tip the scales toward clotting and vascular damage. And then, of course, weight loss, particularly reducing visceral fat, can lower PAI1 levels, which is one reason why losing even a modest amount of weight can have some substantial benefits for heart health. Now, in conclusion for that little section, PAI1 is even less well known than adiponectin, both of which are less well known than leptin, but it is a critical piece of the puzzle, which is why I wanted to highlight it as one of these key hormones. Now, having mentioned these big three, and another fat-focused scientist could say, well, Ben, you should have focused on these ones. Let's talk about some of the other ones. Now that we've talked about these few that I wanted to really have a heavy-handed view with, let's briefly touch on a few of the others just to give you a sense of the scope. So one of the other ones that I very much could have focused on, and will now briefly, is resistin. Now, you might know where this is going already. As the name suggests, resistin is linked to insulin resistance. It's thought to interfere with insulin signaling quite directly, making it harder for cells to respond. Resistin levels tend to be higher in obesity, particularly visceral fat, and it may contribute to the development of type 2 diabetes. Now, at least part of the mechanism whereby resistin promotes insulin resistance is an increase in ceramides, that same bioactive lipid I'd mentioned earlier. Now, the exact role in humans is still less clear. Most of the evidence is in animal models, but it is one other example of how fat tissue can disrupt some metabolic harmony. Next, we have tumor necrosis factor alpha, TNF-alpha. This is one of the more famous pro-inflammatory cytokines in the body in general, and one of the more famous ones produced by fat tissue. As an aside, if you'll allow me to share a personal indulgence, it's this finding that fat cells produce TNF-alpha that first got me fascinated by fat tissue. And in fact, in the show notes, I am purposefully citing that study by the Hotomas-Legill group. It's the one that really piqued my interest and absolutely put me on the path that I'm still on. My fascination in fat tissue was born from the realization that fat produces inflammatory proteins, and that inflammation promotes insulin resistance. And of course, other things like atherosclerosis and even affecting in other aspects, immune function. But it's just one more hormone, a cytokine, but that's a hormone, that's a protein signal that is higher as fat mass goes up, especially visceral fat. Okay, finally, let's mention one more, and it's a complicated one. So maybe we're going out on a bang here in the list of these hormones, but I just want to mention it just to perhaps suggest to you how complicated all of the endocrinology of fat tissue is. This one is angiotensinogen. That's a lot of syllables for one single hormone. Angiotensinogen. It's a precursor to a hormone called angiotensin II. That's a hormone that regulates blood pressure. Now, fat tissue, particularly visceral fat, produces angiotensinogen, which can then act to raise blood pressure by constricting blood vessels and promoting the retention of sodium from the kidneys. So now we have another variable that's influencing heart health, whereas we have the PAI1 that's directly promoting the retention of clots, thereby increasing stroke risk and heart attack risk. Now we have this angiotensinogen production, which can act by promoting the stimulation of the renin-angiotensin-aldosterone system, which I've talked about before, but you can certainly look it up for more details. But the results of which will be to tell the blood vessels to narrow, to constrict, which is pressing in more, which would increase blood pressure, but also telling the kidneys to retain more sodium and water too, which is going to increase blood volume, once again increasing or contributing to a higher blood pressure. Now, these are just a handful of the roughly 50 adipokines identified so far. Okay, now let's shift gears and talk about brown fat for a minute, because it is a unique player in this story. Unlike white fat, like subcutaneous and visceral, brown fat is specialized for thermogenesis, meaning it burns energy to produce a different energy, heat. It's packed with mitochondria, which is actually what gives it its unique color. And as humans, we have more of it relatively as newborns. And then as adults, we start to lose it. However, we do retain small amounts, and we can activate it. We can activate the brown fat with, for example, cold exposure. Now, brown fat does produce some adipokines, and it's generally quite distinct. For example, brown fat secretes fibroblast growth factor 21, or FGF21. This is a hormone that will not only enhance fat burning throughout the body, but also improve insulin sensitivity. Also, brown fat can produce cytokines like TNF-alpha and some interleukins, but much, much less than you'd get by mass from other fat depots. Now, let's just talk, while there are other hormones, I want to just transition quickly into the thyroid role. It's a really fascinating aspect that brown fat plays a critical role in thyroid hormone metabolism, specifically in converting less active T4 into more active T3. So specifically, thyroxine, or T4, is the inactive form of thyroid hormone, while triiodothyronine, or T3, is the active form that drives all of the typical metabolic processes that we think of, from things like just body heat to the conductance of a signal along a neuron, helping things like reaction speed. Brown fat expresses high levels of this enzyme that will mediate this conversion. And when brown fat is activated, say by cold exposure, the conversion ramps up significantly. A 2014 study by De Jesus and colleagues in the very good journal, the Journal of Clinical Investigation, showed that cold activated brown fat dramatically increases T3 production. In fact, it might be the main source of T3 when it's active in the body. If you look at all of the origin of T3 when the body's been shivering and is cold, it's very possible in some people that most of it is coming from brown fat. Now, this brings us all of this to an important question as we near the end. Do the different fat depots, subcutaneous, visceral, and brown, produce different hormones? Absolutely yes. And it's a big reason why where you store fat matters as much as, if not more than, how much you store. Subcutaneous fat, the fat under the skin, is generally the least harmful. It produces higher levels of leptin and adiponectin, which, when functioning properly, support healthy metabolic function from appetite regulation to insulin sensitivity. Also, subcutaneous fat will produce lower levels of pro-inflammatory hormones and, in fact, be more anti-inflammatory. Visceral fat is the opposite. It's more of a troublemaker. Now, that doesn't mean it's inherently bad. It just plays a different role. It's generally promoting more inflammation and more insulin resistance through things like resistin. And then, of course, brown fat is much more involved in metabolically favorable hormones like FGF21 and the helping, if you will, with the conversion of thyroid hormone. So the depot-specific differences can explain why visceral fat is linked to higher risks of diabetes, heart disease, and other conditions, while subcutaneous fat is less harmful, and brown fat might even be the most beneficial of all. So it's not just about fat quantity, but rather fat quality and location. All right, so what have you learned today? Fat tissue is not inert. It's not this just passive depot waiting to be told how many calories to store and how much to release. It is a bustling, busy, essential endocrine organ producing dozens of hormones and possibly hundreds. Endocrine textbooks from even a decade ago had no chapters devoted to fat tissue, but this is actively changing. I can state that as a professor who teaches a class in endocrinology. Now, we've covered some of the big players like leptin, adiponectin, PAI1, but also touching on some others like resistin, TNF-alpha, angiotensinogen, and many, many more that affect myriad immune, inflammatory, metabolic, and cardiovascular processes. The differences between the fat depots matter, but again, the location probably matters more than the overall amount. My hope is that you walk away from this episode appreciating the complexity of fat tissue. I have often said that as a fat scientist, I'm a great defender of fat, that very much our view too often is one of vilifying fat tissue, and I just want to provide some nuance in its defense. It is more than just about aesthetics or energy storage. Fat tissue is a key regulator of metabolic health via its effects on the overall endocrine system. So next time you hear someone dismissing fat as just some extra weight, I hope you'll share a little bit of what you've learned today and maybe join me in defending fat tissue a little more vigorously than people do. Thanks for joining me today in the Metabolic Classroom. If you've enjoyed the episode, please share it with someone who's interested in fat tissue and even endocrinology, and join me next time. Until then, more knowledge, better health.